Hello everybody, welcome to today's video. In our last video we covered graphs of sine and cosine. Today we're going to cover the rest of them. So we'll be going over the graphs of cosecant and secant. And being able to graph cosine and sine will be very helpful in graphing those functions. So if you aren't familiar with those already, I'd recommend doing that first. And then we'll talk about the graphs of tangent and cotangent on the coordinate plane. We'll look at characteristics for all the different graphs. And then we'll also look at finding the trigonometric equation from a given graph. So let's get into it here. The first thing we're going to do is look at graphing the cosecant function. So the cosecant function is the reciprocal of the sine function. So I'll just write this here for right now. This is 1 over sine of x. So what I've got here is just all of the values for sine of x listed out, and we'll just look at taking reciprocals for each of these. So for the first one, if sine is equal to 0, well, then the cosecant is going to be undefined because we can't do 1 over 0. 1 over 0 is undefined, so cosecant will be undefined at 0. If I look at the reciprocal of 1/2, we're going to get 2. If I look at the reciprocal of square root of 2 over 2, we will get 2 over the square root of 2, and we could rationalize that denominator, but we'll leave it for now. What is important here is for us to know that that's about 1.4, because we're going to want to try and graph this on the coordinate plane here in just a second. The reciprocal of square root of 3 over 2 is 2 over the square root of 3. And for what that's worth, that is about 1.2. We'll use that when we graph here, and then the reciprocal of 1 is just 1. And as I go back down the other side here, I'm just going to put in our approximations because this is what we're more or less looking for here, so we can graph some values. And this will give us a half of a period here. And then to get the rest, I'll just quickly fill in the graph. This is going to be -2. This is going to be about -1.4. This will be about -1.2. That is -1. This is about -1.2, about -1.4, oops, -1.4. This is -2, and then we'll be undefined again. Write that a little better. Undefined. There is something on the, there we go. Okay, so now we'll go through and plot these points here. So let me get my reminder out of the way. So we know that at 0 it's undefined, which will correspond to a vertical asymptote. So we'll get a vertical asymptote in at 0. And then we know at pi over 6, so let's get some other values in here on our scale. This is going to be pi over 4. And then to each side of that, we'll have pi over 6 and pi over 3. And we can quickly just kind of sketch in some of these other values. We'll know that the pi over 4, or 3 pi over 4 in this case, will be right in the middle, and then we'll have the pi over 6 and pi over 3s to each side there. So just kind of roughly getting some other hash marks in here so that we can graph stuff. We know at pi over 6 will be up at 2, so there is 2. We know at pi over 4, this will be about 1.4. So we'll look at pi over 4, and that'll be just a little less than 1.5. And then at pi over 3, we're looking at about 1.2, so that'll be just a little bit more than 1. And then at pi over 2, we're at 1. So this is where the graph of cosecant and the graph of cosine will actually, or I'm sorry, the graph of sine and the graph of cosecant will actually kind of intersect each other there. And then we'll go back the other side here. So at 2 pi over 3, we're at about 1.2 again. At 3 pi over 4, we're about 1.4 again. At 5 pi over 6, we'll be up at 2. And then at pi, we are undefined, so we're going to have another vertical asymptote at pi. And if I connect the dots here, we'll see that we get something that looks like this guy here. So we are getting asymptotically close as we approach 0 from the left and pi from the right. We'll see a little bit later that this is actually what's going on. We're kind of hand waving that for the moment, but when we talk about the tangent, we'll see that this is actually happening and things are blowing up to positive infinity in this case around those tangent lines there. So let's see what's happening on the other side of pi. So now we at 7 pi over 6, we want to have a value of -2. So -2 is going to be down here. There's 7 pi over 6. At 5 pi over 4, we're -1.4, so that is about here. At 4 pi over 3, we're -1.2, which is about there. And then at 3 pi over 2, we are at -1. So there's -1, and then it'll turn around on the other side and come back down. And then at 2 pi, we'll have another vertical asymptote since it is undefined there. So here we have just kind of the upside down version of what we saw on the other side there. So if we wanted to keep going, we would have another vertical asymptote at 3 pi. We know that at 5 pi over 2, these will have the same value, and it will have a shape that looks something like that, and this will just be repeating. So we got one full period between 0 and 2 pi, and now I'm just using that shape to keep extending them down. Then if we wanted to squeeze something in, we could squeeze that in there as well. So here we have the graph of the cosecant function. It is very helpful to know the sine function, and then we can just graph this on top of it. We know that where the sine function is equal to 0, the reciprocal function, the cosecant, will have vertical asymptotes. And where the sine function is equal to 1, the cosecant function will also be equal to 1, and where the sine function is equal to -1, the cosecant function will also be equal to -1, and those are their shared points where they turn around, and you can kind of see if like one is laying on top of the other or balanced on top of the other, and that's what we'll use to quickly get these graphs sketched out once it's time to do that. So let's take a look at the characteristics of this graph here. So now not just of the cosecant, but of the full version. Some we called it amplitude before. There is no amplitude now, but this will correspond to some vertical stretch or compression. We've got some shifts, we've got some period compressions, and we've got some vertical shift here as well. So we'll go through all the pieces here. Here I just have the standard old cosecant function graphed against the sine function, so you can see one that's a little bit better looking than maybe the one that I just drew by hand. That's the origin right there at 0. There is no amplitude since we're not looking at something that's bounded. The amplitude is looking at, like, you know, between what values, like how high up and down is this thing deviating from some center position. But that's not happening here. Things are blowing up to positive infinity and down to negative infinity. There is still some stretching factor though, so it's not like we just ignore the value in front. It's just not called our amplitude anymore. Now it's just our stretching factor, just like it would have been in any other function that we saw previously in this class. The period is still 2 pi over b, just like it was before. The period is still 2 pi long. We'll divide it by b in case there are any sort of horizontal stretching or compression to see if our period will also stretch or compress. The phase shift is c over b, just like it was before, and that'll go to the right if c is positive, and it'll go to the left if c is negative. Notice that there's a negative up here though in the way that we're setting this up, and that is important to the way that this goes. The domain, so this is something that is kind of weird, but this is just telling us where the vertical asymptotes are. So this is saying that it's going to be focusing just on this portion here. Every pi over b, so if we're just thinking about b being equal to 1 in the normal case, then it's just at every pi. We've got one at 0, we've got one at pi, we've got one at 2 pi, we've got one at negative pi, we've got one at -2. So we're looking at multiples of pi. That's what the n on there is telling us, that just multiples of pi is where we would have vertical asymptotes. But then we'll want to divide that by b in case there's any sort of horizontal compression or stretching. And then there might be some sort of horizontal shift as well. So that shift is corresponding to the c over b value. So what this whole thing is saying now, if I erase all of that, is that we're still kind of looking at multiples of pi, but then we're dealing with the compression or stretching, and then we're dealing with the shifts to show exactly where our vertical asymptotes are. It's not necessarily important to have this memorized. We can figure it out from when we graph these later, but we're just stating it explicitly here since that can sometimes be helpful. The vertical shift is the d up and down, just like it is before. We're adding some value to the end of our function after we, evaluate it, and that will just move the output either up or down depending on if d is positive or negative. And then the range here, so this is something related to the stretching factor, so it's going to move things up and down, so that's why we see the negative absolute value of a and the positive absolute value of a, and then we're adding d to that since that is going to be our shift up and down, and then they're either going down to negative infinity or they're blowing up to positive infinity. So some very mathy looking notation on here. I think it's easy to get lost in some of this cumbersome notation, but once we apply these going forward, hopefully the intuition is there to kind of not be so terrified of some of this cumbersome notation. It's, like I said, it's not important to memorize every bit and piece here, but understanding the general concepts that, you know, the period is however long the period normally is, which is 2 pi often divided by b, gives us the period stretch and compression, that sort of stuff. So next we'll take a look at graphing the secant function. So we will do exactly like we did before. I have the values for cosine listed out here, and we'll look at taking the reciprocals of all these values, and we'll get something plotted out here, and we'll see a shape that looks very similar to what we saw before, since the graphs of sine and cosine are so similar but shifted over. We'll see that the graphs of cosecant and secant are very similar but shifted over. So let's take a look here. The reciprocal of 1 is 1. The reciprocal of square root of 3 over 2 is 2 over the square root of 3. And we saw before that that is about 1.2. So our goal here is to get things approximated in and sketched in. So that's why I'm looking at the approximations here. This will give us reciprocal of square root of 2 over 2 is 2 over the square root of 2, which is about 1.4. Reciprocal of 1/2 is 2. The reciprocal of 0 is undefined. So this is going to tell us that at pi over 2, we're actually going to have a vertical asymptote. So anywhere on this graph where cosine is equal to 0, 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 we know we're going to have a vertical asymptote, because if cosine is equal to 0, then the secant is undefined. So we can sketch in all of these vertical asymptotes straight off there. You can also see that these are happening at odd multiples of pi over 2. Which is something important to when we talk about what the domain must be here. So just like before, we'll have some sort of c over b that'll correspond to a shift, and some b that'll correspond to some compressions that will change where these vertical asymptotes occur. We'll talk about that when we get there. Let's continue looking at our reciprocals here. The reciprocal of -1/2 will be -2. Reciprocal here is going to be about -1.4. This will be about -1.2. This is -1, and then we'll turn around and go the other way, about -1.2, about -1.4. This is -2, and then we're undefined again. 2, about -1.4. Square root of 3 over 2 is about, I'm sorry, that last one was positive. I was just on autopilot for half a second. This one will be positive 1.4. This one is about positive 1.2, and then we'll have 1 again. So let's get these points graphed in here. So if I'm looking back where we started, at x equals 0, we know the secant will be at 1. So we are starting at the same place that the cosine would start here, but instead of heading down, we're going to start heading up in the other direction. So to get some of our intermediate values plotted in here, here's pi over 4, here's pi over 6, here's pi over 3. We know at pi over 6 will be at about 1.2, and then about 1.4, and then we're at 2. So on this side, we're going to be going up like that. And since we said that this graph is going to look very similar to the one before, since sine and cosine are so related in the way that their graphs look, secant and cosecant are the same. So we could just go plot in these values and see that the other half of this looks like this. We also know that secant is an even function, so it has this reflective property across the y-axis. So lots of different reasons for why we can just fill in this other side here without having straight up seen those values yet. But we'll keep going down our list here. So at pi over 2, we are undefined. And then at 2 pi over 3, which is going to be this guy here, we're going to be down at -2. So now we're down here. And then we're going to be about -1.4, then about -1.2, and then at pi we're going to be at -1, and then on the other side it'll turn around and go the other way. And we'll have something that looks about like that. So there is one full period going from -pi over 2 to 3 pi over 2 to maybe just finish what we've got going on here. I'm not graphing the rest of these values exactly, but now we've got the general shape. This is going to look something like that, something like that. So here we've got the graph of the secant function. We see that it looks a whole lot like the graph of the cosecant function, but just shifted over left by pi over 2. So we'll take a look at the characteristics here. Everything is exactly the same as what we saw before, except where the domain is, because our vertical asymptotes have been shifted over by pi over 2. But the stretching factor is still the absolute value of a. Here we're looking at the full secant function here with all of the transformations applied. But the stretching factor is still absolute value of a. There is no amplitude. The period is still 2 pi over b. The normal period length would be 2 pi, and then that dividing by b would help us either stretch or compress that period. The phase shift is still c over b, and if c is positive, we shift to the right. If c is negative, we shift to the left, just like we've done with every other function. Here's the thing that is different, that the domain is now not at multiples of pi, but at odd multiples. So 2n plus 1 corresponds to odd numbers. Think about plugging in numbers for n. If you plug in 0, you get 1. If you plug in 1, you get 3. If you plug in 2, you get 5, etc. So no matter what value of n you plug in, you always get an odd number. So we're always multiplying some odd number by pi over 2. And that's also being divided by b to correspond to some stretch or compression in the horizontal direction. And then the c over b corresponds to that horizontal shift. So we are still looking at odd multiples of pi over 2. And then those b's and the c over b are just helping us deal with shifting and compressing things as well. So that's where our vertical asymptotes are, or where to find our domain. Vertical shift is still the d value at the end, up or down, and then the range, just like the last one, is going to have to do something with the amplitude of the the amplitude of the reciprocal function, kind of pushing where these values are going to bottom out at or top out at, either up or down, and then they'll blow up to positive infinity or negative infinity after we vertically shift as well. So again, very mathy notation. It's easy to get lost in some of the cumbersome notation here, but the intuition is there. If you spend time thinking about it, all of this says exactly what you want it to say. So, all right, next we will take a look at an example here. Now that we've got the basics of the graphs of cosecant and secant under us. So let's take a look here. What we want to do for these is not try and just straight find the equation that we're looking for, but we want to find the equation of the reciprocal function, because that's traditionally a little easier to find. We've already got the practice in that and the intuition in that. So what we're going to do is just sketch in a graph of the reciprocal function. And since we don't know what that is yet, I was going to maybe take a guess, but let's not go there yet. But I'm just seeing that, like, I know that they're going to share a point where this function bottoms out, and it'll share a point where this function tops out. So I've got these points here where I know my reciprocal function will hit, and I know that it should go through some midline halfway in between these points. So halfway in between pi over 4 and pi over 2 is pi over 3. So I know that it will cross through there, and I know that it'll cross through here, and I know it'll cross through here, and here, and here. So it's looking at odd multiples of pi. It's going to cross through the, well, it won't, actually, I take it back. It won't be going through the origin, because it looks like we're shifted up a little bit. So if we take a look at our midline here, here's our midline. So this is halfway in between. If I go 2 up and 2 down, then that's halfway in between. So now let me get in those other in-between points. It'll pass in halfway through there, halfway there, halfway there, halfway there, and halfway there, halfway there. Okay, so now I've got things marked in a little bit better. So if I want to graph my reciprocal function, it looks like this. So not the one we're asked to find, but we already have practice in doing this portion, so let's use what we already know how to do. So our amplitude here, so we're looking at the yellow function. We'll go back and get the other reciprocal function in just a minute, but the amplitude is going to be 1/2 times the absolute value of the maximum, which is 3, minus the minimum, which is -1. So the maximum value of 3, minimum value of -1, -1, 3. And so this is going to give me 1/2 times, that should be absolute value, of 4, which is 2. So our amplitude is 2. I kind of already predicted that before. I'm trying to get this midline roughed in there. But now we've got the amplitude being 2, so I can say amplitude is 2. I'll just put a little cloud around that, so this isn't the answer, but it is a portion of what we might need going forward. So this is just to quickly find all the pieces that I need as I go forward. Next, we'll take a look at finding the period. So the period is always 2 pi over b. If we do a little bit of algebra on that, we can solve for b, and we'll get that b is equal to 2 pi over p. So we can use this now to figure out what our b value is. So the b value is going to be 2 pi over, and let's figure out what our period is. So if we just go from top to top or trough to trough, we can figure out how long our period is. We'll look top to top here. So I'll just maybe change color. I'm looking at, here's a top that's happening at 0. Here's a top that's happening at pi over 4. Here's the top that's happening at negative pi over 4. So I can see that this distance is pi over 4. This distance is pi over 4. Our period must be pi over 4. So now we know, oops. Our period is, not pi over 4, 4 pi. Our period is 4 pi, not pi over 4. Our period is 4 pi. So 4 pi is our period. And if I simplify that, we just get 1/2. So now we know that our b value is equal to 1/2. We'll put a little cloud around that guy. It's not the answer we're looking for, but this will be a portion of it later on. All right, let's figure out what our phase shift is now. So the phase shift is going to be equal to c over b. So now's usually a good time to decide what sort of function we should be looking at in terms of either sine or cosine. And since this is starting, let me change color here maybe. Since this is starting up, topping out at 0, just like cosine would, I think that this looks a whole lot like a cosine function that hasn't been shifted at all. So I'm thinking that if I'm going to start writing this, this should look like y equals a cosine bx minus c plus d. And since this isn't shifted as all, we know that c over b must be equal to 0, which tells us that c must be equal to 0. So, if some fraction is equal to 0, we don't care what the denominator is as long as it's not also 0. We know that it's 1/2, so that's fine. And so if you get something that's equal to 0, then the numerator must be equal to 0. So here we've got a c equal to 0, which makes sense. There is no shift here. So we've got that. We don't necessarily need to write that in here. And then the last piece of information that we need is the d value. Here we've got a midline of y equals 1, and that is d. So there, I don't want to put a box around it, but I can put a little cloud around it to help put this all together here. So if I would like to tell you what the yellow function is now, then this is going to be y equals, a is equal to positive 2. Since we're not reflecting, we've got a positive a value. Cosine, b is 1/2, x, c is 0, and then d is 1. So this is giving us the yellow function. What we want is the reciprocal function. What we want is these guys. We want the ones that are in purple. So what we don't have is the cosine function, but we have its reciprocal, which is the secant function. So we know that y is equal to 2 secant, and everything else is the same. 1/2 x plus 1. So there we go. We've got the function that we were asked to find. Our strategy is to use the reciprocal function, which we already should know how to do by just piecing all of this information together about the a, b, c, and d values, and then just switch to the reciprocal when we write our final answer out. All right, next we will go the other way. So here we are given a secant function, and we will graph it ourselves on this coordinate system here. So let's go through this, and we're not going to try and graph the secant function straight up, just like we did before. We are going to graph the reciprocal function first as a guide, and then we'll go put the secant function on top and below that. So what I want to look at here is not the secant, but at 4 cosine pi over 3x minus pi over 2 plus 1. So let's just get everything that we need here. The a is going to be 4. So that is an easy thing to find there. Next, we want to find the period. The period is going to be 2 pi over b, and b is pi over 3. Maybe save a little bit of space, right? It is pi over 3. And then if I cancel things out here, this is going to give me 3 halves. Yeah. I'm sorry, that's going to give me 6. I'm getting ahead of myself. But yeah, pi's are going to cancel. Reciprocal 2 times 3 is 6. There we go. So the period is equal to 6. The phase shift is c over b, which in this case is going to be pi over 2 over pi over 3, which this is going to give me, pi cancel, 3. This is 3 over 2. I knew it was coming eventually. So there's our 3 over 2 for our phase shift. So this is going to be shifted over 3 over 2, or 1.5 radians. Everything here is in terms of radians. And then our midline is going to be, so the midline is going to be y equals 1. So this is going to be shifted up 1 unit. And then we want to use information about 1 full period in order to kind of figure out where things should be in here. So we're going to use 0 less than or equal to bx minus c, so just the argument of our cosine function here, pi over 3x minus pi halves is less than or equal to 2 pi. So we're just sandwiching our argument, the argument of our function here, or the cosine function, same one in both spots, but we're sandwiching it between what 1 full period would be, which is 0 and 2 pi. And if we solve for x here, this will tell us how things have been squashed or stretched. And so just to save a little bit of the algebra, what we get from this is that we get 3 halves less than or equal to x less than or equal to 15 halves. So this tells us that 1 full period is going to occur between 3 halves and 15 halves. All right, now that we know where 1 full period will occur, we'll get some reference marks in here so we can start getting stuff graphed in. So we'll make that 1, 2, 3, 4, 5, 6, 7. There's 8. So in between that is going to be 15 halves. And then over here, maybe I'll do these in just a different color just so we can reference them, because these are important points to us. So this is going to be 15 halves here, and then 1.5, that's 3 halves, is there. So we know that 1 full period should occur between these two values. Maybe I'll just write in a few more numbers here just so we have them. Okay. So now what we're going to do is get in the in-between points. So we know that we want to split this period from 3 halves to 15 halves into 4s, into quarters, so that we can get the top point where it goes through, where it comes back, or the bottom point where it comes back through and where it tops out again. So we want to find all these in-between points so that we can start to graph in just a basic cosine function that is shifted and stretched horizontally appropriately. So what I'm going to do here is I want to find this distance. The way that I can find that distance is by looking at 15 halves minus 3 halves. And then if I want to split that into quarters, I will multiply that by 1 quarter. And if I simplify here, I'll get that this is equal to 3 halves, which this is telling me that every 3 halves, I want to put another key point on here. So I will start at 3 halves. I'll go over 3 halves, which will put me at 3. So there'll be a key point here. And if I'm thinking about what the graph of cosine should look like, it would start up at 1 at 3 halves. That's where cosine starts. And that means that it will go through 3 here, and then it would bottom out another 3 halves over. So another 1. So here is going to be another key point. This is where it would bottom out. If I go over 3 more halves, that'll be here. This is where it'll pass back through. And if I go over 3 more halves, I should be back at 15 halves. So if I want to sketch in just a very basic cosine function, we have not stretched our amplitude at all, and we have not shifted up and down at all. So this is just a very basic cosine that has been shifted a bit, just so that I can see where 1 full period lives. In our next step, we'll go through and we'll get the rest of it here. So let me maybe move some of this important information here that we found about 1 full period. Oh, I missed my 15. That's okay. just so we still have it. That's a 15. This is a full period. Okay, so I'm just going to clean up my work that I did over here so that we can get in our graphs. Okay, so we want to graph in now this cosine function that has been moved up, because we want to move it up 1. Where is it? Our midline is at 1. So if we go through, we can put our midline at 1. And then we want to have an amplitude of 4. So that means we're going to go up 1, 2, 3, 4 from there. So that's up at 5. And then we want to go down 1, 2, 3, 4. So down at -3. So this will be where this tops out and bottoms out at. The midline is our midline. These things aren't exactly proportional here. Let me... 1, 2, 3. That's a little bit better. So down at -3. Okay, we know that our graph now, maybe I'll do this in, whatever, it doesn't matter. We'll keep it, let's do blue. We know we're going to start up at 5. We know we're going to cross through our midline at 3. We know we're going to bottom out at 4.5. And then we're going to go through our midline at 6. And then we're going to top out again at 15 halves. So this is, again, not the one that we're trying to graph, but the corresponding cosine graph should look like this. And it would keep going. If I want to find another point here, I'd go over, this will go over 3 halves here. So I'll turn around, do something like that, come down like this, and do something like that. So there's our corresponding cosine graph that has been stretched, shifted, shifted, everything. We've got all the vertical and horizontal compression shifts, etc. So now what we want to do is graph the related secant function. So wherever this is going through its midline is going to be where it is undefined, because that corresponds to passing through 0. So these are all of our vertical asymptotes. There'll be one more over here somewhere. But if I want to graph this in now, we know that they share a point where cosine maxes out is where secant bottoms out, and where cosine bottoms out is where the secant tops out. So we'll get something that looks like this. So there we go. We've got our secant function graphed here. The strategy is to just graph the corresponding reciprocal function and then use that to graph the secant function on top of it. If we wanted to, maybe we could go back and erase some of our other scribbles here. Maybe it's a good idea just to show. Oops, I got too much there. Not totally necessary, but if I just want to clean that up a little bit. So there we go. All right, next we will take a look at graphing the tangent function. So we're going to do just like we had done before with taking a look just by plugging in values, just straight graphing stuff in here. So before we're looking at reciprocals, we'll do that next maybe when we look at the cotangent. But here I'm just straight plugging in values, and I already have a lot of them pre-populated in here so that we can take a look. But we know that at -pi halves we're going to be undefined, so I can put in a vertical asymptote there, and I can see at pi halves we're also going to be undefined, so I can put one in there. So here we have just a period of 1 pi that we're looking at. So we'll see that more as we go forward. I've left some blanks in here because I want to take a look at what's happening around this vertical asymptote at pi halves, so that we can build some intuition that, yeah, it's actually blowing up to positive infinity and zooming down to negative infinity around there. So we saw that happening on the previous graphs. I want to just show that more explicitly here. So let's get some values graphed in here. That's pi over 2. This is going to be -pi over 4. This will be -pi over 6. And -pi over 3. Ooh, that's pretty sloppy, but we've got them in there. Maybe I just won't write the values since there's not a ton of space down there. But we'll have values on either side there. There's pi over 4, and there's the values on either side there. So at pi halves, we're undefined. At pi over 3, we're at negative square root of 3, which I should have written down what some of these values are. Maybe I did. I did. This is about negative 1.7. So we can use that fact to our advantage. Negative square root of 3 divided by 3 should be about a third of that, which is negative 0.6 we'll go with. Just rounding a little bit there. Then this will be negative 0.6. This will be, oh, not negative anymore. Now we're positive, sorry. Just 0.6. 1, of course, is 1. And then this would be about, this is also about 1.7. And then we're undefined again over here. So if I plot these points in, negative 1.7 for negative pi over 3 is going to be around there. At pi over 4, we're at negative 1, so that is there. We're at negative 0.6, that's there. And then we are at 0. And then it turns around, and then we're at 0.6 again. And then we are at 1. And then we are at 1.7, which is about there. So we can see it's kind of got this little bit of a cube root shape going on. Cube root would totally flatten out before it goes back up, but it has a little bit of that shape going on here. And what I want to show now is that this does indeed just keep zooming up to positive infinity here, because we're just kind of skipping from 1.7 all the way to undefined, all the way to just, you know, there's nothing there. But I want to show that these values are getting larger and larger as we go. So if we just started plugging values into a calculator, if we looked at the tangent of 1.54, we would see that we would get about 32.5. So, you know, as I get really close, we're already like way up there as I'm getting very close to pi over 2. And then as I put in 1.56, I would get about 92.6. So yeah, this is indeed getting very large. These numbers are getting super big as we're getting closer to pi over 2, where it becomes undefined. And then we'll see on the other side here, if I tried to put in negative 1.58 into a calculator for tangent, we would get negative 108.6 about. So of course that's going to be way down there somewhere. And then negative 1.6 is about negative 34.2, which is still way down there. But, you know, the idea is that, yeah, it is zooming up to infinity on the left-hand side of this asymptote and is going down to positive or negative infinity on the right-hand side of that asymptote. So we can see that something similar would be happening on that side as well. So here is one full period of the tangent function. If we want to get the rest graphed in here, we'll get another vertical asymptote at 3 pi over 2. We'll get another one at negative 3 pi over 2. And then we'll just have this general shape where it'll flatten out and then keep going up. Flatten out around the midpoint and keep going up. So there we go. Then we've got the graphs of tangent here. You can see the vertical asymptotes occur at the odd multiples of pi over 2. So I'm sure we'll see that on this page here. So now we're looking at just characteristics of the graph of any old tangent function that's been stretched, compressed vertically, horizontally, shifted vertically, horizontally. So just like before, there is no amplitude. Our numbers aren't, or our function values aren't trapped in between a couple of points, and they haven't been stretched. In that regard, things are going off, function values are going off to positive and negative infinity, but they still might be stretched by some factor a. So we still have this here, but just like before, there is no amplitude. The period now is not 2 pi over b, because the period of the tangent function is just pi. So in order to deal with that stretching or compressing, we will still divide that by b. So just something important to notice is we're not doing 2 pi over b for these, we're doing pi over b, since the period for the period for tangent is just pi. The rest of this should look very similar though. C over b is our phase shift. So just like before, if C is positive, we go to the right. If C is negative, we go to the left. The domain, just like one of the previous ones that we saw, we're looking at odd multiples of pi over 2. And then we are stretched or compressed by b and shifted by C over b. So we're still getting odd multiples of pi over 2 in just our basic graph before we start shifting and compressing. The vertical shift is still d units. Here the range is easier to see because we don't have these gaps like we did for secant and cosecant. It is just from negative infinity to positive infinity. We hit all values there. So there's our characteristics of the tangent graph. Next, we will take a look at the cotangent graph, and we will do this somewhat quickly here. We just have a few of the key values because we're going to see a graph that looks very similar. This will be shifted over a bit from what we saw for the tangent function. So at 0, we're undefined. So if I'm just putting in my vertical asymptote, and then at pi, we're undefined. And here we're going to see that at every multiple of pi, so not odd multiples of pi over 2, but just multiples of pi, we get our vertical asymptotes. If I get some values plotted in here at pi over 6, we're going to be, this is about 1.7. This is about 0.6. So at pi over 6, we're going to be about 1.7. So let's get these values in here. There's about 1.7. Here is 1. Here is about 0.6. And then at pi over 2, we're at 0. And then I'll turn around and go the other way. So we'll be at about 0.6 there, 1 there, 1.7 there. So here we're going to get a similar shape to what we saw before, but it is just reflected a bit. So here they're going from the bottom to the top from left to right. Here they're going from the top to the bottom from left to right. So if they've just been reflected a bit, and then we can get similar shapes here for all of the in-betweens. Something like that. Not my best graph, but I think that you probably get the point there. That one's definitely not good at the end, but okay, something like that. But they should all look identical. So let's take a look at what it should look like. There's a nice graph of it. So again, just our basic cotangent function. Again, no amplitude, but there is still a stretching factor of a. The period is still pi over b, so cotangent and tangent both just have a period of pi. The phase shift is still c over b. Here the domain is just multiples of pi, and then we'll divide that by b to account for any horizontal compression or stretching, and then we will add c over b to that to account for any horizontal shifting. So very similar to what we saw before. Vertical shift is still the vertical shift, and the range is still negative infinity to positive infinity. We can see that all values are attained within just one period here. Okay, so what we will do now is graph. Here we're given a cotangent function, but the idea for both cotangent and tangent is the same. So now we're not going to graph the reciprocal function because that doesn't make sense in this situation. We're just going to find where some consecutive vertical asymptotes are. That'll give us one full period. Then we'll find the spot right in between and use that to just rough in our shape here. So depending on if we're given a tangent function or a cotangent function, we'll solve a slightly different inequality here. Remember that tangent has one full period going from negative pi over 2 to pi over 2, and cotangent has one full period going from 0 to pi. As long as you remember that, all we're doing here is just putting bx minus c in between one full period, and you could really pick any period you want, but these numbers give us something that's kind of nice. So the situation that we're in is for cotangent, so we'll be looking at this guy here. So in order to get our vertical asymptotes, what we're going to do is look at 0 less, well, not equal to, 0 less than x plus pi over 4. We're not putting equality here because we have asymptotes on the endpoints. We can't include them here. Less than or equal to pi, so we will subtract pi over 4 from everywhere, and we will end up with negative pi over 4 less than x less than 3 pi over 4. So this tells us where one full period will be. Let me just erase this here and maybe move this over here or something. So this tells us where one full period will be. So between negative pi over 4, so here's negative, whoops, here's negative pi over 4. We're going to have a vertical asymptote there. And we're going to have another one at 3 pi over 4, which is here. And I know that one full period should occur between those two values. So now that we've got our vertical asymptotes in here, what we want to do is plot an x-intercept halfway in between the asymptotes, and then we'll just rough in our shape here. So we want some point that's somewhere in between here, and we could possibly see where that is exactly. But to compute it explicitly here, what I want to do is just find the average in between these 2 points. The midpoint of any line segment is just the average between the endpoints. So what I'm going to do here is just look at the average. We'll do pi over 4 plus 3 pi over 4, and we'll divide that by 2. All right, if you want to find the average between 5 and 12, you add 5 plus 12 and divide it by 2, and that'll give you the average. We're just doing the same thing here. And so if I add those together, I'll get 2 pi over 4, which is, well, yeah, I'll just write it out. 2 pi over 4, all divided by 2. And this will just end up being pi over 4. So now I know that our midpoint here is at pi over 4. And I think, like I said, we could have probably guessed where that it is just by using some symmetry of the situation here. But now that I'm looking at a cotangent function, I know that it'll start up here and it'll pass through there and then head down in that direction. I'm not worrying too much about getting some of these intermediate values in there kind of close to pi over 4. If you want to, you can go and compute some of those to get them roughed in, but we're just trying to sketch a graph here in my opinion, and so that that doesn't correspond for me to getting things exact here because we just want to use the graph. So let me get in some more horizontal or some more vertical asymptotes here. Since this is going to have a period of pi, we are just shifted here. We are not compressed at all. I can just get in another one by going over another pi over, so that'll be here. I'll have another one. If I go this direction, I'll have one here. And then I can just get in a few more. Oh, I don't know that this one's where I want it to be. 3 pi over 4. And then I want to go over 3 pi over, yeah, that seems okay. We'll get something that looks like this. This one's a little big over here. I don't think I counted this one properly. I want to go over, there's pi over 4. There's another pi over 2. Oh, yeah. There we go. All right, there we go. We have got our graph of cotangent in here. The idea is just to get one period roughed in there. We find the midpoint in between them, get that shape in there, and then you can build the rest around that. All right, with that, I will leave you to practice. So good luck with the homework. Please let me know if you have any questions. I'm always happy to help. See you in the next video.